foldable electric three-wheeled cargo vehicle chassis is now complete. Starting the selection process for the 5-spoke integrated alloy wheels and mechanical brakes. 4 engineers use calipers to accurately measure the diameter of the front axle assembly. Next is sorting the telescopic suspension forks with hydraulic shock absorbers, carefully checking the stroke length of the forks to calculate the ground clearance of the vehicle. The U-shaped triple tree is checked for concentricity before being assembled with a front fork. The curved motorcycle handlebars are also prepared ergonomically on the workbench. The engineer test fits the steering system on a flat surface to shape the design. The step of fabricating the steering neck, the load-bearing steel tubes and tapered bearings are brought out to check the tolerances. The fit between the bearing race and the steel tube wall must be absolutely tight to prevent play. A mechanical vise is used as a static press to push the bearing into the steering neck tube. Using a wooden block helps distribute the force evenly, preventing scratches and cracking the bearing race. The central steering stem is then inserted through the neck tube to create a smooth rotating joint. TIG welding with argon shielding gas is used to tack weld the stem to the triple tree. The handle BU0061RS are accurately centered and fully welded solidly to the top of the steering tube. The electric motor, a foldable BLDC type, is mounted directly into the 2 dropouts of the suspension fork. Using a wrench to tighten the axle lock nuts, completing the entire front steering assembly. The fabrication process of the main chassis begins with rectangular steel box sections. The 45-degree beveled corners are butt welded using a high-power arc welding torch. 2 reinforced steel gussets are added to the blind corners to prevent torsional deformation. A high-speed angle grinder smooths out the fish scale welds, optimizing the surface of the shock absorber assembly. A single coil spring, strut with hydraulics, is test fitted into the center of the frame. Starting to machine the support base bar, the engineer welds shut a small rectangular steel tube. 2 axle bushing tubes are coaxially positioned and welded fixed to the crossbeam, supporting the fork. A marker and a square are used to mark and space out the drilling distances. On the steel flat bar, a drill press pierces through the steel blank to create U-shaped mounts for fixing the top of the shock absorber. Passing the bolt axle through the holes of the U-brackets to complete a movable T-joint. Starting to assemble the elastic edge, attaching the bottom of the coil shock absorber to the truss bars. The entire suspension assembly is placed onto the rectangular frame, base, and fixed in position with bolt mounts. The engineer welds the upper U-shaped mount fixed onto the thick, longitudinal beam of the main frame structure. Continuing the operation, arc welding connects the lower mount of the shock absorber directly to the frame wall. The support base for the steering neck at the front is positioned perpendicular to the T-beam, temporarily locked with a clamp after removing the mounting jig. The engineer test fits the height and calculates the caster angle of the front fork, proceeding to bevel cut a steel gusset plate, creating a high-strength right trapezoid load-bearing part, reinforcing the V-shaped gusset plate, connecting the steering neck column and the longitudinal frame beam with solid TIG welds. The front subframe now has a triangular structure with excellent resistance against braking and folding. The rear axle guide frame then needs to be equipped with 2 synchronous drum brake wheels, preliminarily checking the diameter of the wheel hubs, and the steel box tube that will serve as the rear load-bearing axle, performing longitudinal marking lines to accurately determine the hole centers for drilling on the drill press. An accurate drilling path through 2 layers of steel U-channel forms the mounting position for the long axle bolts, linearly pairing the 2 U-beams, rectangular steel together to increase the bending resistance cross-section. Tack welding the edges deeply along the steel body, creating a specially solid horizontal beam. Next, fabricating the lever arms and auxiliary levers from short-cut square steel tubes, grinding and rounding the edges to integrate the hinge joint of the mechanical folding pillar. The angle grinder continues to round the ends of the square steel tubes. In preparation for the hinge folding joint, the 2 beams are placed perfectly end-to-end. The steel leaf hinge is test-fitted into position. The TIG torch tightly secures the hinge to the beam surface, creating a flexible double folding joint, checking the smoothness of the fold, ensuring the 2 steel frame branches fold perfectly parallel. Next is the core component of the electric cylinder mechanism, also known as a linear actuator. The engineer checks the base length of the pushrod, analyzing the maximum extension stroke parameters, connecting the RF control circuit to the lead-acid battery pack, carefully connecting the positive and negative terminals correctly, plugging the cylinder signal jack into the receiver, setting up the 3-button remote control. Pressing the button activates the internal DC motor to rotate, driving the lead screw to smoothly extend and retract. The extension and retraction stroke is thoroughly checked, ensuring the pushing force torque meets the design level. Removing the power source, the electric cylinder is test-fitted onto the newly fabricated hinged U-frame module. The engineer proceeds to measure on a flat steel bar, marking parallel and evenly spaced horizontal lines. These will be the power transmitting lever arms, using a tri-square to accurately mark the center for drilling. The cylinder feeds the steel billet into the drill bit at high speed, piercing the marked positions to create pinholes. The sharp alloy drill bit creates concentric round holes, meeting the exact tolerance dimensions of the bolts. Preparing thick steel U-brackets, inserting the pivot bolt through the bracket hole and the cylinder's mounting arm. Assembling and positioning the bracket assembly onto the steel beam, aligning it correctly with the longitudinal centerline of the entire cylinder. Deep tack welding connects the support bracket to the frame bar. The basic motion structure begins to take shape. Expanding the 2 lever arms of the steel frame assembly, extending the cylinder rod to measure the diagonal distance, using a tape measure to get the actual dimensions. To calculate and cut the moving X bracing bars, continuing to cut short and drill holes on the steel plates. To fabricate the age mechanism, a multi-point mechanical scissor age, bolting the 3-way age of the bracing bars to the cylinder head. This is the main pushing force focal point of the entire system. The remaining 2 ends of the bracing mechanism are screwed directly into the 2 expanding frame branches, secured with anti-slip lock nuts. The rotary joints require low play, but must absolutely not bind. Manually testing the folding mechanism. The cylinder operates as a central lever to fold the 2 arms. To optimize the lifting and lowering force, they utilize an additional 2 gas springs to assist the mechanical power. Removing the stock plastic caps to fabricate circular eye joints from solid punch steel and welding them directly to the hydraulic rod. Simultaneously welding U-shaped hook eyes onto hollow steel tubes, creating a metal outer casing to protect the gas spring rod. TIG-tack welding requires high technical skill, so the heat does not burn the rubber seal inside the strut. Assembling the steel guide tube over the gas strut. We now have a telescopic elastic support strut system that is perfectly smooth, inserting the connecting pin of this hydraulic strut into the S-axis, creating a flexible deforming parallelogram structure. Placing this assembled transmission cluster onto the rear axle frame base, proceeding to align with an angle square to ensure symmetrical geometric distances. The TIG torch strikes an arc, securing the resting points of the hydraulic struts to the outer rectangular beam frame base. When the electric cylinder retracts, the gas struts are compressed to store energy, making the outward push process much smoother. This complex and synchronized cross-bracing system helps convert the linear motion of the day cylinder into a dual folding angular motion, preparing a flat square milled steel plate, tack welding the mounting brackets, and bolting U-bolts onto the flange. This thick flange will serve as the mounting base in the entire folding assembly. To the front T suspension tractor module, tightening the gas strut's tail locking pin to the mainframe base, assembling the 2 chassis modules together through the solid steel central hinge pivot pin, inserting the thick pivot pin through the connecting brackets, unifies the tractor head and the folding tail mechanism. Install the yellow dual spring shock absorbers. Securely weld the U-shaped bracket onto the steering column. Attach the sporty cast aluminum wheels to the rear axle. Tighten the axle bolts securely to fix the suspension system. Turn on the power for the linear actuator. Use the RF remote to start the real-world folding mechanism test. The age system perfectly retracts the wheelbase, narrowing and expanding smoothly without delay. To attach the ergonomic leather-wrapped seat, and the engineer tests the seating posture, checking the bounce of the dual shocks. Moving on to fabricating the cargo box, welding together the square steel tubes to create a rectangular base frame. Use an angle grinder to remove burrs and weld spatter on the flange surfaces, creating a perfect contact area. Measure and cut cold rolled steel plates for the floorboards. Tack weld reinforcing strips to bear the chassis load. Continuously weld a secondary rectangular frame. Continue grinding the edges flat to ensure safety. Surface treat the steel base plates of the cargo box. Divide the floor into two halves to accommodate the folding mechanism. Use self-drilling screws and a cordless drill to attach the steel hinges, connecting the two halves of the cargo floor. The longitudinal hinges make folding the floor in half easy. This mechanism optimizes storage space. Install 8 frame locking hinges. Install sliding spring latches to secure the floorboard when laid flat. Test the sliding locking latches. Begin fabricating the surrounding box walls from pre-cut thin steel plates. Position the 4 side walls and tack weld small butt hinges to connect the metal walls together. TIG welding arcs deeply melt the contact surfaces. The box walls form a flexible, articulating edge. Drill and insert screws to add extra stability to the hinges. Fold the walls to form a hollow rectangular box. Use magnetic angle clamps to position them at exactly 90 degrees at the corner joints of the box walls. Screw in the corner hinge latches and install safety sliding bolts to lock the box in a rigid square structure when in use. The box walls are highly mobile and easy to fold up. Moving on to the assembly stage of the power source with a powder-coated metal battery box. Place 4 12 volts lead-acid batteries into the box. Check the safety insulation pads at the bottom of the batteries. Use a screwdriver to tighten the copper ring terminals. Wire the battery pack in series up to 48 volts. Connect the large cross-section power cables, quick connect plugs, and the BMS signal wires for safe charging and discharging. The frame is powder-coated in striking colors. Screw the flat steel plate in place as a footrest. Place the central battery box onto the chassis mount. Screw it down tightly to prevent shaking during movement. Finishing up the braking system. Install the mechanical brake levers, made of aluminum alloy, onto both sides of the handlebars. To route the steel core brake cables down to the front drum brake assembly, and mount the turn signal control switch assembly on the handlebars. Fine-tune the tension of the front brake cables. Tighten the locking nuts on the drum brake levers to ensure responsiveness. Connect the waterproof power plugs that transmit high current electricity from the battery box to the hub motor. Open the battery box cover to make a final check of the wiring diagram, the BMs, battery terminals, and plug in the main signal connector. Activate the entire powertrain electrical system of the 3-wheeled vehicle. Close the battery box cover in preparation for the test. The brushless motor drives the front axle. Twist the Hall effect throttle, sending the signal to the control ike, and the front wheel starts spinning rapidly. The BLDC motor responds extremely fast. The RPM is stable, with no loaded vibration. Use a cordless drill to securely fasten the bolts holding the rim assembly deep into the expanded rectangular frame system. The hexagonal cargo box is unfolded and mounted directly onto the rear frame base, fitting perfectly down to the millimeter. The engineer gets on the vehicle and activates the chassis folding mechanism. The rear cargo box extends incredibly smoothly. Starting the outdoor load capacity test. The 48 volts motor delivers impressive traction on the road. Stop the vehicle and test the retraction mechanism. The linear electric actuator retracts the axle, pulling the rear wheel assembly and folding the box walls. From a long cargo cart, the device transforms into a compact mini electric 3-wheeler. Test driving in the folded mode. The short wheelbase provides a tight turning radius for nimble maneuvering. The wide caster angle steering mechanism, combined with grippy fat tires, helps the vehicle corner safely at high speeds. The frame has good torsional rigidity. There are no mechanical squeaking noises during operation. Heavy load testing with large carton boxes. The hexagonal compartment space optimizes excellent storage capacity. 4. Use elastic cargo straps to securely tie down the cargo and prevent shifting while driving. The dual front fork and independent rear suspension system absorb all vibrations, keeping the cargo extremely stable. Upon arriving at the drop-off point, the engineer quickly unloads the cargo. A perfect last-mile delivery solution. This electric folding design is truly a breakthrough in applied mechanical engineering.